Recording in progress. Hi students, in this lecture I am going to discuss center of mass. Let us see first list of concepts. So first we discuss definition, then position vector, velocity vector and acceleration vector of center of mass, then law of conservation of momentum. After that, calculation of center of mass. So taking a circular or semicircular plate, hemispherical shell, hemisphere, solid cone, and hollow cone. And after that, we discuss finally center of mass frame, means the advantage of solving questions from center of mass frame and how to solve. That is the last one. So let us now focus on the first one, that is definition of center of mass. See definition part. For a system of particles, there exists a point where we can assume the entire mass of the system and we can assume all forces are acting at that point to study the translatory motion of the system. Let us see in detail. Consider a person throwing a uniform rock by one end holding one end of the rod. When he throws, we can find one point in the rod which is following parabolic path, because different points in the rod are following different paths. But you can find one point which is following parabolic path. This is what we have learned in kinematics. If you project a body, means oblique projectile, path is parabolic. So that point which is following parabolic path, that point is called center of mass. That means for that point, it is only translatory motion. It is only translatory motion. So throughout the motion of the rod, we can find one point that is following the parabolic path. Maybe rod is like this, maybe rod is like this, maybe rod is like this. Whatever may be orientation, but one point will be always on the parabolic path. So center of mass, even we can say like this. It is the point for which there is only translatory motion, right? If you remember earlier, if a block is moving, we have taken block as a point mass. The relation was when block having translatory motion, each and every point having same displacement, same velocity, same acceleration. That's why we have replaced the body with a point, and that point is nothing but center of mass. So we can assume entire mass at its center, means at center of mass, and we can assume all forces are acting at center of mass. Okay. Suppose if distribution of mass is uniform, let us take a triangular plate. If distribution of mass uniform, centroid will be center of mass. That means in case of symmetric bodies, geometric center will be center of mass. Suppose I am taking a uniform ring. For uniform ring, center of mass will be at its center. And remember here one important point. At center of the ring, there is no mass. That means at center of mass, there need not be any mass present. Okay. And one more thing here, center of mass always within the boundary. We cannot expect this center of mass outside the boundary. It is always within the boundary. I will take one more example, like imagine we are throwing a ball means we are rolling a ball on ground. When ball is rolling, we can find center of mass is following now straight line path, means it is having only translatory motion. So center of mass, how to identify means it is the point for which there is only translatory motion. And whenever we want to focus translatory motion of the body or translatory motion of the entire system of particles, replace them with a point mass and assume entire mass is present at that mass at that point and assume all forces are acting at that point. Okay. Now we have to focus how to know the location of center of mass. How to know the location of center of mass. Let us see how to get location of center of mass. Center of mass location is given by R bar Cm. Position vector of center of mass is given by M1 R1 bar plus M2 R2 bar and so on upon total mass M1 plus M2 plus M3 and so on. So this is giving us position vector of center of mass. If you want x coordinate, xm is equal to m1 x1 plus m2 x2 plus and so on upon total mass. That means what we are doing here is multiply mass of one particle with its position coordinate. Take like this for each and every point mass. Okay. If we have, if distribution of mass is uniform, so this is for system of particles. Okay. Means distribution of mass is not continuous. If distribution of mass continuous, this can be written as xm equal to integral x dm upon integration of dm. So in fact, these two are same only, meaning wise, only notations are changed. So here we're having number of particles. Distribution of mass is discrete. Okay, this is now distribution of mass continuous. So x and dm. Just consider one point mass. Its mass is dm. And x is its position coordinate. Multiply. Next, take one more point mass. Multiply with its position coordinate. Then take sum of all these things. Okay. And in this, coming to dm. If you are taking dm for linear bodies, it is taken as lambda into dx, or you can say dl, where lambda is mass per unit length, where lambda is mass per unit length, or it is also known as linear mass density. Linear mass density. So we are taking a small length dl. Its mass is lambda into dl. If you are taking a two-dimensional body, it will be equal to sigma into ds. Now you can guess what is a sigma. It is mass per unit area. Okay, no? This is a two-dimensional body. Or we can say surface mass density. Sigma is surface mass density. And if you are taking three-dimensional body, like solid cone, or it is solid sphere, there we consider volume density, means mass per unit volume. Okay, that's the way of calculating dm. And after having position vector, if we multiply, if we multiply, sorry, after having position vector, if we differentiate that, we are going to get velocity vector for center of mass. That is m1 v1 bar plus m2 v2 bar plus and so on upon total mass m1 plus m2 plus and so on. Students, if you observe carefully, the upper one means numerator m1 v1 momentum vector of first particle, m2 v2 bar momentum vector of second particle. If we take sum of all those things, that gives momentum of the system, which is equal to total mass into velocity of center of mass. So advantage is no need to calculate velocity of each particle. If we know velocity of center of mass, multiply that with mass of the system. That gives momentum of the entire system. Okay. Next, differentiate once again. Differentiate once again. That gives acceleration of center of mass m1 a1 bar plus m2 a2 bar plus and so on upon m1 plus m2 and so on. Okay. See carefully m1 a1 bar. It is net force acting on first particle. Students, if you remember, in laws of motion we have learned net force is equal to mass into acceleration. It is now m1 a1 bar net force on first particle, m2 a2 bar net force on second particle. Now take sum of all these things. That gives net force on the system, which is equal to total mass of the system into acceleration of center of mass. It is total mass of the system into acceleration of center of mass. So here what I can write is F net. F net is equal to total mass of the system into acceleration of center of mass. Okay. Now here we can say one condition. If net force, if net force on the system is zero, students, we have learned that net force is equal to rate of change of momentum, right, with respect to time. Then we can write momentum of the system is constant, is constant. This is known as LCM, law of conservation of momentum. So I'm repeating, if net force on a system is zero, then momentum of the system is constant. Why means because net force zero means dp bar by dt. Net force is rate of change of linear momentum with respect to time, right? Net force zero means dp bar by dt is 0 bar. That implies p bar of the system is a constant, which is known as law of conservation of momentum. Okay, right. Let us now focus some more important points here. Right. Okay. Now see what we can do here. For example, on a system, net force equal to zero. On a system, net force equal to zero. So when net force is zero, acceleration of the system is zero, right? Acceleration of center of mass zero means velocity of center of mass is constant, and that constant may be zero or may be non-zero. If you remember, this is the statement of Newton's first law. If net force on a particle is zero, then its velocity remains a constant. Or we can say its motion, or we can say state of motion remains the same. That means we can use Newton's laws of motion as it is for center of mass. Okay. Suppose question given like this. Net force zero and velocity of center of mass zero. Condition given that velocity of center of mass zero. Net force zero. Net force zero means ACM zero. ACM zero means velocity constant. Now condition given that BCM zero. Okay. BCM zero means what I can say here, shift in center of mass is zero. Delta R bar CM equal to 0 bar, right? Because condition is given that net force is 0, velocity of center of mass 0. Net force 0 means acceleration of center of mass 0. So velocity of center of mass does not change, and that value given 0. That means VCM is always 0. That means center of mass does not move. So shift in center of mass, or you can say displacement of center of mass is 0. Okay. Displacement of center of mass 0. So if you are taking two particles, for example, we are focusing x coordinate, then what I can say here, delta xcm equal to 0, right? So delta r bar cm 0 means delta xcm 0, delta ycm 0, delta zcm 0. Now I am focusing delta xm 0. Its meaning is delta xm is equal to m1 delta x1 plus m2 delta x2 and so on upon total mass. Okay, m1 plus m2 plus and so on. When delta xm 0, numerator is 0, right? Means I can write here m1 delta x1 plus m2 delta x2 and so on equal to 0. See, when we are writing this condition, BCM 0 and net force also 0. BCM 0, net force also 0. Therefore, BCM is always 0. Means center of mass not moving. Therefore, shift in center of mass will be 0. I hope you got the logic. Okay. Right. Now let us focus. Let us focus in case of two particles, how to know location of center of mass. Already we got R bar Cm equal to M1 R1 bar plus M2 R2 bar and so on by M1 plus M2 plus M3 and so on. Let us now apply that in case of two particles. Let us take two particles, M1 and M2. Separation between them, take it as R. Assume that these two are now on x-axis. Okay, assume that these are on x-axis. So now what we can do? We want to locate center of mass. Center of mass location. Assume that it is somewhere in between these two. Its distance is now R1 from M1, R2 from M2. Okay. Now see how to get R1 and R2. So I want to use now M1 R1 bar plus M2 R2 bar and so on. Okay. And I'm saying that assume that these two are on x-axis. These two are on x-axis. Then see what we can do. If we want to find out center of mass distance from M1, assume M1 is at origin. Okay. Then what happens is x1 equal to 0, x2 equal to r, right? See carefully. I want to measure distance of center of mass from M1. So I'm taking M1 is at origin. When M1 is at origin, x1 0. Then M2 will be, it is x2 equal to r. Now write condition, xm equal to. It is now nothing but r1, right? I will write here. We are measuring distance from first one. So R1 equal to M1 X1, M1 X1 plus M2 X2. X2 values are upon M1 plus M2. So we can get it directly. No need to by heart any formulas here. If you want to find from M1, take M1 is at origin. M1 is at origin. Then R1 equal to M2R by M1 plus M2. Okay. Suppose you want to calculate from M2. Then what I'm saying is take M2 is at origin. M2 is at origin. Then what happens is M1 into R plus M2 into 0 upon M1 plus M2. Okay. So this is now M2R by M1 plus M2. Okay. This is equal to M1R by M1 plus M2. So in case of two particle system, separation equal to R, then distance of center of mass from M1, that is R1, which is equal to M2R by M1 plus M2. Okay. Next, coming to R2, means distance of center of mass from M2, that is equal to M1R by M1 plus M2. So we are going to use these two frequently in our problems. Okay. So I hope you got a clarity here. What we have done, first we have taken definition of center of mass. Okay. And after that having VCM, ACM, then net force. If net force is 0, momentum of the system is constant, which is known as law of conservation of momentum. And next we have taken here one condition like if VCM 0 and net force 0, then VCM constant. Center of mass does not move. So shift in center of mass is 0. So delta xm is 0. Then we can write m1 delta x1 plus m2 delta x2 and so on equal to 0. Then for two particle system, how to find distance of center of mass from m1 and from m2. Okay. In the next lecture, we can discuss problems basing on this.